Hey folks, so today I'm going to talk about quantum proofing Ethereum and some of the problems, the ideas, and a potential solution that might be interesting for you all to implement. So to get started, I will kind of do a brief breakdown of what exactly are powers of a quantum computer, uh, what exactly in Ethereum and other blockchains like Bitcoin breaks, and what are some proposed solutions, and what is the solution that I think is most practical, which requires the least migration, which is namely to use ZK Starks as a signing mechanism for ECDSA. So a good place to start is what are the exact powers of a quantum adversary? We can go more into detail, and I've linked a couple of videos that do, but the high-level idea is that due to Shor's algorithm and Grover's algorithm, you have now a machine that can extremely quickly take prime factorizations and take discrete logs. What they cannot do is undo a hash. So a hash is still a one-way function. And the problem with this is that given a public key, they can derive a private key. And so this is what leads to all the secret keys on any blockchain system being leaked. Now, it turns out that the way blockchains work is that they have a public identifier, which is your address corresponding to your public key. This is actually the hash of your public key and the first 4 characters. Now, interestingly enough, because, like I said, hashes are quantum resistant, it turns out if you have only revealed your address and not revealed your public key, aka the thing that you use to sign transactions, then no one can actually reverse engineer your secret key from just your address. And so we use this key insight to derive a method of proving that you are doing a transaction that corresponds to some address without revealing the public key. So we can dive a little bit into annealing versus qubit computers, but the high-level idea is that while annealing computers claim large qubit values, they don't necessarily get anywhere near that level of performance in practice on difficult problems. And so more likely the qubit quantum computers will be the ones that break cryptography as we know it. And it seems like IBM is well on track to do that sometime between 2030 and 2015 is my current guess, but it's unclear. I go into some specific bounds that help define what the different algorithms are and how they work, but this won't be super relevant for this specific project. Now, it turns out that some parts of zero knowledge will be broken. So for instance, ZK snarks will be back secure, meaning you don't know past information that has been privately proved. However, in the future, anyone can generate a fake ZK snark for any statement. And so we can't actually use ZK snarks. But as you know, there's 2 main kind of ZK protocols, snarks and starks. The primary difference is that, well, there's many differences, but one difference is that starks are much faster to generate and have much larger proof sizes, but many of them are quantum proof because they rely on hashing, versus snarks rely on usually either discrete log, well, mostly discrete log, and so they would not be quantum secure. Turns out that because Bitcoin is built on UTXOs, it's actually slightly easier to make quantum secure, but regardless, that's not our focus right now. We'll be talking about Ethereum. But I do think the Bitcoin project is still a compelling idea. Now, there's a number of proposals for how to do quantum-proof cryptography, and most of them require using lattice-based cryptography or other post-quantum schemes, which would result in everyone having to migrate their entire Ethereum systems. So you mean all smart contracts have to be rewritten. The entire way that you interact with the chain has to be rewritten. So a much better solution is keeping all of the address-based properties of Ethereum. People can even keep addresses that they haven't yet interacted with the chain yet, and then use, instead of direct ECDSA signature, which is what you use to verify that you're in fact sending some transaction, we send a ZK Stark proof of that ECDSA signature. There's a couple of key components that we'll need to implement the system end-to-end. 3 components are a wallet interface, So this basically means like there should be a way for me to sign a transaction that is a standard Solidity function call data, with the difference that instead of signing the transaction and sending it on chain, I instead am signing it locally, creating a ZK Start that I in fact signed it locally, and then proving that on chain. It might be easiest to use a simple burner wallet for this for proof of concept, or you could try forking an open source wallet to do that. The second thing you'll have to build is an account abstraction system. The idea is that you'll have to verify the ZK Start signature and then execute whatever Solidity function is trying to be executed on chain. There's a number of templates like this ETH infinitism trampoline one that are easy to get started with this. And finally, there are some functions that use the public key on chain. Remember that if we are trying to quantum proof an account and allow them to send transactions, then we can only reveal the address, not the public key, and obviously not the private key. And so you can see, think of the public key now as this kind of quantum insecure key. If we reveal it, then our account can be broken, but only by quantum computers. And so the problem is anywhere that your public key is revealed, we have to deal with those situations independently. And so places that use EC Recover on chain, for instance, would likely have to be monkey patched in some way. And all the accounts that have previously called EC Recover on chain and that value has been stored somewhere would have to fix that storage or migrate that storage or make that storage somehow invalid. And so you would have to have some utility that allows you to call most smart contracts. And this is more of a nice to have, but you can either monkey patch EC Recover to ensure that there's a new function that is called that identifies the address instead, or you can just check the contract that you're calling doesn't use EC Recover and then continue to call it. The main things that I think will be interesting here are functionality. So a simple demo where I can make a simple transaction and it sends via a Start proof with account abstraction on chain. Number two, security. All these proofs need to be generated client side. It defeats the purpose if it's generated on the server because then the server knows my public key and therefore my private key via a quantum computer. And so again, one of the trade-offs with ZK Starks is that because the proof sizes are larger, the verification takes longer than, for instance, the standard Groth16 verification. And so it will likely be a little bit too expensive for an L1, but is probably practical in an L2. And finally, one of the strengths of ZK Starks, especially compared to Snarks, is that they're very fast to generate. This is changing a little bit with more recent schemes, such as folding schemes, or things like Lasso Jolt. But regardless, Starks should still be pretty fast client side. So I expect speed to be quite good. You should, in the ideal case, be able to run this on a mobile phone as well. Sweet. So I've added a bunch of links to different things that might help you understand these problems more in case this video wasn't enough. Things like a non-technical intro, a technical breakdown, a video by Veritasium that he actually released about 5 months ago, showing that kind of via the RSA algorithm and how it works, putting quantum computers into that context, explaining the basics of Shor's algorithms, and showing how you can use things like entanglement to break this algorithm. The animations are beautiful as usual. So that video is also quite interesting, but not quite as relevant to the system you'll be building here. If you have any questions, let me know. I'm excited to be mentoring these projects. And hopefully you guys build some super cool stuff.